All right, so this is the factoring using quadratic techniques video. So pause it if it's moving too fast for you, but we're going to go and go through some of this worksheet here. So the first thing you need to copy down is the degree of a polynomial. The degree of a polynomial is just the largest exponent when the problem's in standard form. So for instance, 1a and 2a ask what is the degree of each quadratic? Well, you simply just look for the largest exponent. So the largest exponent for both of these problems is 2. So that means the degree equals 2 for both of these problems. The question also says factor the following quadratics. That's just old review problems. We're going to skip that for now. So we'll be factoring some more problems as we move our way down through this worksheet. So as you're going through these problems, ask yourself, first off, does the problem have a GCF? You're still looking for greatest common factor when you do these problems. Of course, there's a few things here to write down as we go through. Make sure you're copying everything down here in the notes. So the first thing you look for, of course, is the GCF. The second thing you look for is you look for a quadratic doubling pattern. So what does a quadratic doubling pattern look like? Well, you look for the largest exponent. So if you look at this first circled quadratic, the largest exponent for this problem is a 4, and then it is double the next largest exponent. So 4 is double 2, so that means this can be factored. This polynomial can be factored. And you look at the second example, the largest exponent is 6. Well, that 6 is double the middle exponent, 3, so it can be factored. It's following that quadratic doubling pattern. And this final example you see does not follow the quadratic doubling pattern because 5 is not double 3. So the largest exponent has to be double the middle exponent to be able to be factored. So that third one would be prime, and you can't factor it. And then finally, other methods to consider. You can only factor using the perfect square method if it is a subtraction problem. So a squared minus b squared, you can use the perfect square method to factor that. That would be factored as a plus b and a minus b. This last one over here, a squared plus b squared, that cannot be factored because of that plus sign in the middle. So if you have two perfect squares but with an addition sign, that's going to be a prime product. It cannot be factored. So look out for that. That will pop up frequently today. All right, so the main thing, let's go to the main event, and let's go ahead and work on factoring each of these problems. So we want to factor each expression completely using quadratic techniques. So the first thing you're going to do when you look at number 1 is look for a GCF. There's no greatest common factor. They have nothing in common. So you're going to go straight to method number 2. You should notice that there are 3 terms. So anytime there's 3 terms, you're going to use the box method. So this is just, for the most part, this is pretty similar to what we've done in class already. There is a slight difference though. But the first term is x to the 4th. It goes in the first box. -5 is the last term. It goes in the last box. You take the first number, you multiply it by the last number. We're looking for 2 numbers that multiply together to give us -5 and add together to give us that middle number, +4. So there's only 2 numbers that will multiply together to give you 5, and it's 1 and 5. You just have to make sure you get the signs correct. 1 times -5 gives you -5, and, well, I think I've got my signs backwards. Let's make 1 negative and 5 positive, because -1 plus 5 is 4, and -1 times 5 is -5. So those are the 2 numbers that go in the box. The only difference here is, instead of a -1x and a 5x, we're going to look at that middle term and see that it has an x squared. So these terms are going to be x squareds instead of just regular x's. And then factor the GCF out of each row and each column. The first row, You can factor out an x squared. The second row, you can factor out a 5. This first column, you should be able to factor out an x squared. And the last column, you should be able to factor out a -1. So the factors we have here are x squared plus 5 and x squared minus 1. However, we can go a little bit further. X squared minus 1, you should notice, those are both perfect squares. The square root of x squared is x, and the square root of 1 is 1. Remember, to factor perfect squares, always one of those is a positive 1, and one of those is a -1. X squared plus 5 those are not perfect squares. In any way, it's a plus problem, so you cannot factor x squared plus 5 further. So this is your complete answer for number 1. That's what it means to completely factor the problem. Do not leave the problem at this step, because that's not completely factored. Go ahead and try number 2. I'll get you started. 4x to the 4th goes here. 5 to 9 goes here. Remember to take the first number and multiply it by the last. You're looking for two numbers that multiply together to give you 36 and add together to give you -13. So go ahead and pause the video, see if you can do this one on your own, and then press play to see the answer. So this should be your initial step. -9 and -4 are the two numbers that multiply together to give you +36 and add together to give you -13. But you shouldn't notice, you can go further on both of these. Both of these are perfect square problems. So 4x squared minus 9, the square root of 4x squared is 2x, and the square root of 9 is 3. So it factors into 2x plus 3 and 2x minus 3. And we already know x squared minus 1, we just factored that a second ago, is x plus 1, x minus 1. So the completely factored answer for this problem. Is right here. 2x plus 3, 2x minus 3, x plus 1, x minus 1. All right, so you should look at number 3. Number 3 is a prime problem because it does not follow the doubling pattern. The largest exponent 4 is not double 3, so number 3 is prime. Go ahead and pause and try number 4. Remember, you need all the answers down. We do have a quiz on this end of the period, so practice this one on your own. Press pause now and press play in a couple of seconds once you get the answer. So here we're looking for two numbers that multiply together to give you 16, add together to give you -17. Remember, you look at that middle term, x to the 4th, so that goes in the boxes with -16 and -1. And then just take the GCF of each row and each column. So the GCF of each row and each column should yield this, x to the 4th minus 1, and x to the 4th minus 16. Both of these are perfect square problems. Difference of perfect squares. The square root of x to the 4th is x squared. Square root of 1 is still 1. The square root of x to the 4th over here is x squared. The square root of 16 is 4. However, you should notice x squared minus 1, we factored this one a few times already. That is still a perfect square problem. So you can factor x squared minus 1 again. X squared plus 1, it cannot be factored again because it is a sum because of that plus sign. Those are both perfect squares, but it has to be a difference of two perfect squares. Same thing for x squared plus 4. Those are both perfect squares, but because of that plus sign, you cannot factor x squared plus 4. But x squared minus 4, we can. It factors into x plus 2, x minus 2. We have a long answer. That's not a long answer as you'll ever see in these problems. All right, a couple more. Number 5. So number 5, you probably notice first glance does not follow the doubling pattern. But don't forget you've got to look for GCF before you do anything else. Number 5 does have a GCF of x. So you can factor an x out in this problem. And when you factor an x out, you're left with x squared minus 9, which you should notice. Those are both perfect squares. So you can factor x squared minus 9 as x plus 3, x minus 3. Don't forget the x that you factored out is part of your answer. All right, number 6. Number 6, same thing. You've got a greatest common factor in this problem. The GCF is x to the 3rd power. They all have an x. The smallest exponent of the problem is x to the 3rd, so they all have at least 3 x's. So your first step in this problem should be to factor out an x to the 3rd. And then what we can do is we can factor 3x squared minus 16x minus 12 further using the box. So pause this one. Try number 6 on your own, see if you can get the answer to number 6. So here's your answer to number 6. Remember, don't forget the GCF that you factored out at the beginning is part of your answer. A lot of you are leaving that off on this past test. All right, pause if you need to, but I'm going to go to the last page here. So I want you to go ahead and try number 7, 8. Number 7 and 8. Try those two problems on your own. See if you can get these problems by yourself before you start doing problems that will be graded. So 7 and 8, see if you can get these correct answers. There's no GCF on 7, no GCF on number 8. So you know you're going to start with the box on 7 and 8. Pause now and try 7 and 8. All right, so there's your answer to number 7. Notice this one does not have perfect squares. Because this 3 is not a perfect square, you cannot factor either one of these further. Same thing here. The 3 is not a perfect square, and really neither is the 2. So this one can only be factored once. Number 8, however, can be factored again. Number 8 initially factors as x squared minus 49 and x squared minus 1, but both of those are difference of perfect squares. Try one more, try number 9 on your own and see if you can get that answer completely correct. Again, no GCF on number 9, so you go straight to the box in that problem. So number 9, there is what the box should look like on this one. You should notice one of those can be factored again, t squared minus 16. T squared and 16 are both perfect squares, so it can be factored again. 5 is not a perfect square, so that one cannot be factored a second time. Last couple that we'll do, number 10. Number 10, there's no GCF, but there's two terms. This may not be one you recognize, but 625 is a perfect square. So if you type in the square root of 625 in your calculator, it should give you 25. So really what this problem is, it's a difference of two squares to start out with. So this factors as 25m squared plus 1 and 25m squared minus 1. 25m squared minus 1, those are both still perfect squares. The square root of 25m squared is 5m. Of course, the square root of 1 is just 1. You cannot factor 25m squared plus 1 because of that plus. Where it has to be a difference of two perfect squares. So this is your final answer. There's no other perfect squares in this problem. Don't try to factor 5m minus 1 because 5 is not a perfect square. So you cannot factor that any further. Pause if you need to. These last two, we're not going to do the last page, but 11 is prime. There's no GCF. It does not follow the doubling pattern. So that first exponent's not double the second exponent. Number 12, you might go initially into perfect squares on number 12, but you'd be wrong because there's a GCF first you can factor out on number 12. You should be able to factor out an n squared. If you factor out an n squared, you're left with n squared minus 49, which then you can use the perfect square method. But again, don't forget the GCF. That is part of your answer. All right, so go ahead and work on the partner assessment. Turn that in. Remember, you'll have a quiz at the end of class covering this section.